Now let's talk about what happens when you have a mass on a spring. Remember, there are two cases. The first case is horizontal. And basically what you have is you have some mass M connected to a spring. And if you extend the mass, a distance delta x, and we'll just use x because it's horizontal. So we're going to stretch this out. So my mass is back here. My string is stretched out. Then the force applied is minus kx. Now, why is it minus? Because the displacement is negative, but the force of the spring is going to be to the right. So that's just a restoring force. That's all that negative sign means. But once I do that, it's going to oscillate. And the period is 2 pi square root of m over k. So the bigger the mass, the faster the period. And the smaller the spring constant, the faster the period. The other case is, what do you do when you have a vertical spring? So here we have a spring, and it's in its happy place. When you add a mass to it, it's going to stretch it a distance delta y. And the y just means it's vertical instead of horizontal. So you have a mass m, you have a delta y. Well, the first thing you notice is it's going to stretch it. And what force is being applied to the spring? Well, of course, the force being applied is the weight of the mass. And this has to equal kx. Don't worry about the negative signs. We could use a y or ky, it doesn't matter which one you use. So from this, you can find the spring constant is the weight of the object divided by its displacement. Once you find the spring constant, the period is 2 pi square root of m over k. It's the same problem. So let's do a couple. If a mass of 0.55 kilograms, so m is 0.55 kilograms, attached to a vertical spring. Okay, so it's vertical. Stretches the spring 2 centimeters. So delta y is 2 centimeters, but you're smart. You're going to go ahead and convert that to 0.02 meters. From the original equilibrium position, what's the spring constant? Well, if you draw a diagram, this is the mass, and here's delta y. You know, Fg equals the force of the spring. So mg has to equal kx. So k is mg over, and okay, fine, it's k times delta y. You can use delta y or delta x, I don't care which. Delta y. So the mass is 0.55 kilograms. G is always 9.8 meters per second squared. You have that. Divided by the displacement is 0.02 meters. And you get that K is 269.5 newtons per meter. Now if I have a 0.75 kilogram mass, okay, I don't like the way I'm doing this, well let me start over. This is my mass, so M is 0.75 kilograms. It's attached to a vertical spring, so this is again a vertical spring. Stretches the spring 0.3 meters, so now delta y is 0.3 meters. What's the spring constant? Oh, okay. So Fg equals F spring. So Mg is Kx. Again, remember you don't have to worry about, and I'm sorry, I keep using x. Hooke's law is always an x to me. All right, so K is mg divided by x. So the mass is 0.75. G is 9.8. And delta x is 0.3 meters. So you get a spring constant of 24.5 newtons per meter. So now we're going to take this 0.75 kilogram mass and we're going to put it horizontal. What's the period? All right, suppose I have a, let's see, mass is 0.75 kilograms and K is 24.5 newtons per meter. Now we know this. I know the period is 2 pi square root of m divided by k. So it's 2 pi square root of 0.75 divided by 24.5. Make sure you do this first. You get a period of 1.0, let's see, what did I get? 1.09877 seconds. Can we just call that 1.1 seconds?